Good day, I'm Dr. T and welcome to my dining room table. So today I'd like to talk about one of the more challenging calorimetry problems that we sometimes do. This is not challenging per se due to conceptual reasons, but because the algebra is a bit of a pain. So in this case, we're going to be looking at two materials. So let's go for some water. So I'll have a container for the water to be in it. And we'll assume this container is nice and insulated so that the heat isn't just leaking out all over the place and this problem is completely unsolvable. So we'll assume it's nice and insulated. We'll assume it's a calorimeter of some sort. And of course, there's water in our container. And I'm going to use a nice blue pin for the water. And then, like quite a few of the other classic calorimetry problems, I'll just go ahead and assume that there is some kind of metal in here. Let's call this lead. Okay, now in this case, what I'm going to know is the mass and specific heat of these guys. So I know right off the bat that the blue stuff is supposed to be water. So the specific heat of water is going to be 4.184 joules per gram degree C. Okay, so the silver thing, I know that guy is lead. So specific heat of lead is known. So I go ahead, I look up the table that's off screen, and that's going to be 0.128 joules per gram degree C. And I'm also going to say that I know that the mass of the water is going to be some value, and we can just kind of make up a value here. I'm going to make it up as 137.3 grams. Likewise, I know the mass of the lead, and once again, it's another number I'm just going to kind of make up. Obviously, if you were doing this, you would be weighing out the lead properly. But in this case, let's say the lead has a mass of, lead's heavy, let's say 257.1 grams. Okay, so we have these guys, and in fact, we also have, starting temperatures. So let's say this before the two are mixed, the lead is starting out at 98.7 degrees C. I don't want to go over 100. That's actually going to make this problem a lot more complicated because then there would be a phase change involved. So right now, I'm going to just assume that we're not going over 100, at least under normal atmospheric conditions. Likewise, the T initial for the water, and I probably should have clumped these up a little bit more organized, but well, it's done. Let's say that is 22.1 degrees C. Okay, so what we're missing here, the part we're looking out for, is T final. Now, the key here to remember is that because these two guys are sitting together in the same vat, they are exchanging heat back and forth. T final is just going to be T final. It is going to be T final for the lead and for the water. It's not going to be its separate thing for each one. This is actually helpful because now we've got one equation we can plug this mass into and we have one unknown. It just happens to exist on both sides of the equal sign, which is why this is a tad bit annoying for the algebra. Otherwise, it's not that bad. Just a pain for the algebra. Okay, so the general layout of this equation, like really any other calorimetry equations, would end up being mass of whatever we're dealing with, say mass of water, times specific heat of the water, or the lead. We can do this either way. Delta T, which is T final, minus T initial for the water, and that's going to equal the mass of the lead times the specific heat of the lead times T final minus T initial lead. And then we have to do a -1, just literally anywhere in that equation. And sometimes you'll actually see them just switch these, one of your delta t's, just switch the order. To me, that gets me every time. I mess it up every time I try and do that, so I just don't. Okay, so we're going to try and find TF. And to do this, let's start by taking this equation and plugging in some numbers. I'm actually going to work down here just because I don't think I left myself enough space up there. So let's see, mass of water, that's going to be, did I give mass of water? Yeah, I did. So that's going to be 137.3 grams. Probably should actually put of water, but I'm going to keep that straight. So it should be good enough. times specific heat of water, which is 4.184 joules per gram degree C. The joules will cancel, or the grams will cancel, not the joules. Then that is times by parentheses TF minus 22.1 degrees C, because that's my TI of my water. And this is actually what's going to start making my life a little bit more interesting, is that parentheses. And so I'm going to have to start unpacking these. And it's going to get a little bit annoying. Okay, then over here, I'm going to have 257.1 grams times 0.128 joules per gram degree C times TF minus 98.7 degrees C times minus 1. And first thing I want to do is just grab my trusty calculator, which unfortunately has had a line die on it. Really was not happy to see that. But it's been a good friend for basically 20 years now. So I have enjoyed this guy. Actually, I've had this guy over 20 years. Got him when I started high school. Okay, so I'm just going to type in these sides, just kind of try and condense things as much as humanly possible so I don't have to deal with them. So 137.3 times 4.184, that gives me, let me repeat that so the line's not in the way, 574.46. Okay, I know I don't have 5 sig figs, so I'm just going to write 5 sig figs that way. I don't have to deal with it. That's joules per gram degree C. No, joules per degree C. The grams have already canceled. And then that's times TF minus 22.1 degrees C. And that's going to equal, I'm going to do the exact same thing for the other side. So 257.1 times 0.128 gives me, the side is 32.909 joules per gram. Nope, just joules per degree C. And that's going to be times, actually that's going to be negative. I almost forgot that minus sign. There's actually going to be a quick check we're going to do at the very end just to make sure we didn't mess up the minus sign. Unlike when you are solving for either the mass or the specific heat and you get a minus sign, oops, and all of a sudden it's going to have a negative number that literally cannot be negative. In this case, you will have a number that potentially looks valid. Therefore, you do have to double check to make sure it is. The difference typically ends up being is your T final will have to be between your two T initials. And if you get your minus sign messed up, odds are it'll be outside of the two T initials. So we'll do a quick double check just to make sure at the very end, once we get a T final, that it makes sense. Okay, so T final minus, and then T initial is 98.7 degrees C. Okay, then I'm just going to clean things up when we're dealing with this. So I'll go ahead, I'll divide both sides by, might as well just pick this side, 32.909 joules per degree C. Those units will cancel. In fact, that whole thing will cancel with that whole thing. That's the whole point of doing that. This side I'll divide it by minus 32.909 joules per degree C. That's going to cancel. That's going to cancel. Which is actually good. We don't want any other units running around. We know that TF needs to be in degree C, and seeing that it's being subtracted from degree C, this is good. This is a very good situation we're currently in. Okay, and I'm actually going to have to do that math. So 574.46 divided by my previous answer, which is second answer, gives me 17.456. So this is going to be 17.456 TF minus 22.1 degrees C equals TF minus 98.7 degrees C. Okay, we've gotten partway here now. We've actually broken apart one of our two parentheses, so we're in good shape. So at this point, I'm actually going to go ahead and distribute this over here. So this will be 17.456 times TF minus, and then I have to do the math on that one. So 22.1 times this guy, second answer. There we go. 385.78. And I've already messed up my minus signs. You see it? I forgot to copy this guy over. So that guy's going to be a negative sign. That guy's going to be a negative sign. That's going to be minus a minus. And when we subtract to subtract, that's the same as adding. And so that's a degree C. And then that's going to equal TF minus 98.7 degrees C. And the end is in sight. Because now all of a sudden, we're going to move this TF over here. In the process, it's going to get rid of our minus sign. So to this side, I'm going to go ahead and add 17.456 times TF, and I'm going to do that to this side as well. As well as on this side, I am going to add 98.7 degrees C. And I'm going to do that to this side. And I probably should have actually grabbed the blue pin just to kind of be clear what we're doing here. Okay, so what's going to happen? So on this side, I add this to that. So that whole thing is going to cancel out with that one. That's not going to cancel. In fact, those two are going to go ahead and add together. So I'm going to get 385.78 plus 98.7, 484.48 degrees C, and that's going to equal, now on this side, the 98.7 degrees C's cancel, so I'm going to be left with 18.456 times TF, and I'll divide both sides by 18.456. And in this case, it's kind of hard to see on my calculator because of that cutoff line, but my number is going to be 26.2505 degrees C equals TF. When I hit the enter again, because there was a second answer in the equation, that caused it to continuing to do the equation. So I can just retype this in number-wise, just in case you're not convinced that I can read my calculator. As you can see, that's the case. It's an interesting quirk with your calculator. You get to know, if you hit the enter twice, it will typically just do the equation again. Had there not been that answer in there, then it would just done it from scratch. But it was doing from the previous answer. Okay, so that's my answer. Well, that's not quite my answer. I need to do sig figs. When it comes to sig figs, okay, 4, 4, that's a 3. Truth be told, we are probably going to be dealing in this range of probably about 2 sig figs. I only have the 1 decimal point over here. So I'm not going to be able to go past the 1 decimal point on that side. So this is going to be 26.3 degrees Celsius will be my final answer. Now, we're going to do that last check to see if I did mess up the minus sign, which is a persistent problem with doing this one. And this is not the first take of this video, let's put it that way. If I have it correct, T initial of whatever my cold one is should be less than T final, which should be less than T initial of the hot one. So, is 26.3 degrees more than the temperature of my water, which is the colder of the two? Yes, that works. Is it less than the temperature of the starting temperature of the lead? Yes, that works. So everything passes through, assuming I didn't make something silly for a mistake, in which case, chuck it in the comments. But I think this should be pretty straightforward. And the algebra is annoying. I will totally admit that for this type of equation. But apart from that minus sign, and that minus sign will get you occasionally, these aren't that bad. So I encourage you to practice a little bit of your algebra, have some fun, and I will see you in later videos.